R2 new minus R0 divided by R0. R0 is the original value. So delta R2 equal to some number minus alpha. So R2 prime equal R0 1 minus alpha, and R1 prime equal R0 1 plus some positive number. Okay, next page. So that's why we can get these two equations, R1, R3. This is original value, We use alpha 1, alpha 2, previous. See, we have this positive number, pi at pi value, stress, pi value, stress. So we have positive sign, negative sign. Okay, next page. So we just use this one to represent pi value and the stress. Pi value and the stress. So we get these two equations. Frank, do you understand? Okay. Then we have Keystone bridge for this pressure sensor. The Keystone bridge, we arrange R1, R3 here, R2, R4 here. So R1, R3, R2, R4 here. And V0 is the output voltage. Vs is the bias voltage. Supply the voltage to this Keystone bridge. Okay, now please calculate this. VO divided by Vs equal to this. Derive this one. After you derive this one, plug in these two expressions into this one and get this solution. Okay? Ready? Go. Next page. Okay, sorry, previous. Okay, next. Then, next. Here is the cross-sectional view of the piezo resistor. Remember, we use doping. We put the dopants, the ions, inside the silicon wafer. And as the dopants diffuse into the silicon wafer, the number of dopants will be, we have another high density of dopants. Then we have low density of dopants. Then their piezoresistivity, sorry, this resistivity raw value is depend on the depth Z. So this is Z equal to 0 and Z positive direction. So different Z value, we have different piezo resistivity. So rho E. Then we have this. This is conductance. This is resistance. So 1 over resistance equal to conductance. 0 means no stress. There's no sigma. So we have original value. But remember, we have voltage applied to this end. And this end is ground. So imagine we have resistor 1, resistor 2, 3, 4, 5. So are they in parallel or series? Either the connection of these resistors, are they in parallel or in series connection? Parallel. Okay, they are in parallel connection. So for parallel connection, their total conductance, we add them to have the total conductance. Okay, so resistivity equal to rho L divided by A, but conductivity equal to A divided by rho L. Now, at the beginning, they have the same resistivity, the same length. Each one has the same length, L, but their cross-sectional area is different, dA, dG, for each differential element. For each element, their conductance equal to their cross-sectional area divided by rho L. But they have the same width. So in this direction, they have the same width, but different thickness. So we use dz to represent the thickness, dz1, dz2, dz3, dzn. dz is the thickness, and w is the width. So w multiplied by dz is the cross-sectional area, dA. So we can put, because total conductance equal to the integration of each tiny conductance. So you can take this integral as a summation of each tiny element. So we put each tiny element dg here. So w dz, rho L. But now rho is a function of the thickness. Okay? Raise your hand if you understand this integration. Okay, you are in charge of these two rows, and you are in charge of these three students. Please explain to them this integration. Camera off. Okay, next page. Then, Kyler, could you read this? Read. Yeah, read.
From where?
Here.
The value of Zj relative to the structure thickness is quite important. Recall that in pure bending, the stress goes from tensile at one surface to compressive at the other. If the piezoresistor goes all the way through the structure, the stress response will average to zero. At the other extreme, if I2 is very small compared to the structural thickness, one can use the surface stress to estimate the response. In practical structure, I2 may not be negligibly small, so stress averaging may be necessary.
Okay, so this one should be Zj. So X is a mistake. Zj. Then for this example, if we bend this beam this way, if I bend the beam this way, so the top surface here, if I bend the beam, if I bend this way, bend, so here would be either here will be tension or compression. Tension or compression.
Compression.
Dad, could you help me? Yes.
So long and this is short. So this is the tensor.
Okay. Tension. Okay, so here will be tension, here will be compression. At the center, zero stress. See, tension, small tension, small tension, zero. Then compression, compression, big compression. So at the center, no stress. But if this is a B, but the piezo resistor, we just near the top we have piezo resistor, and all the other V silicon, no piezo resistor. In that case, the stress in the piezo resistor will be tension only. We can take the top stress as the stress applied to the piezo resistor. If the piezo resistor thickness is small, very small compared to the whole thickness of the B. Ami, do you follow me? Yes. Okay, next page. Then here, see we have a Z coordinate from the top. Z equal to 0 goes down. And the total thickness of the bead is H. H is the total thickness of the bead. Then this is the stress. And stress equal to, see, come back to this equation. Strain equal to 1 over Young's modulus. Stress in L direction minus nu stress in transverse direction and stress in Z direction. So if this is L direction, L, this is my forefinger is L direction, then rotate 90 degrees is the T direction, and the thumb direction is the Z direction. So we have this expression, epsilon L equal 1 over E sigma L minus nu sigma T minus nu sigma Z. For V, under bending condition, we only have sigma L. We don't have stress in this direction. We don't have stress in this direction. So sigma T and sigma Z are 0. So we are left with only sigma L. So L is the stress in length direction. So we can put, so this is sigma L. This is Young's modulus. This is strain, epsilon L. Here, the red square, the everything inside the square is epsilon L. Hang, H-E-N-G. And you are me, M-I-N-G. Me, hang. Huan, H-E-N-G. Hang. Okay, hang. Do you understand this?
Yes.
So epsilon L equal to the distance from the so this is H. So rho is the curvature of the beam, and this is the distance from the center. Distance from the center divided by curvature is strain. So this is center, and the total thickness is H. So this is H over 2. So if we consider this point, so this point, the distance to the center is H over 2 minus this is Z coordinate. So h over 2 minus z is the distance to the center. So distance to the center divided by curvature is strain. This is the strain term. So if z is less than z over 2, so this is positive, means tension. But if z is larger than h over 2, this term is negative. We have compression. Okay, raise your hand if you follow me. Kill Kaiser. Yeah, last. Do you understand? Kaiser. So raise your hand if you follow me. Next page. So this is conductance. So conductance equal to W dV over L rho E. So this one, we have seen this one already. Then rho E 0 means this is resistivity under zero stress. So this one, the mean resistivity with stress, and pi L is piezoresistor. So we have this term. Then rho EZ. Rho EZ, you can put this one here. And let me show you the magic. Can you please help to make it straight? Yes, thank you. Thank you very much. Okay, next page, please. Let's look at this one. See, we put this term over here, W dz divided by L rho E0, 1 plus pi L sigma L. Do you remember Taylor's series? Okay. Based on Taylor's series, if this one is less than 1 plus a very small value, then you can W dz here, L here, and rho E0 here. But this one will become, see, this one is 1 plus pi L sigma L minus 1. But use Taylor's series, you can get 1 minus pi L sigma L, 1 plus pi L sigma L square. Keep going, but because pi L sigma L is very small, the square, third, fourth, compared to first order, we can neglect them. So we are left with 1 minus pi L sigma L. Okay. Next page. So that's why we got this one. Because a previous. So remember we did integration. If we do total G equal, this is one tiny element, dz. But you can do integration with respect to z. Then we can get G. But G equal to 1 over total resistance. Next page. So that's why we got this one. Ethan, do you understand? Good. Then for this one, we have this term. So integration WL rho E0 minus WL rho E0 pi L sigma L dv. But the first term is R0. because W is the constant, L is the constant, and rho E0 is the constant. So you can move everything out for the first term. So you can get W L rho E0 and integration dz. So integration, differentiation cancel out. So this is total thickness H. So this term is the G0, original conductance, and G0 equal to 1 over R0. So that's why we have 1 over R0, the first term. This one is inside. So if this one is inside, 1 over R0, we don't have this one. But you move this one outside, then we have this parenthesis. So this becomes 1. You move R0 out, so you need to put R0 back. Okay, that's why we got this one. So then let's do reciprocal. So reciprocal R0. 1 minus a small value. So this term compared to 1 is small. So if you do reciprocal, 1 minus a small value equal to 1 minus this small value minus 1. So minus 1, we get plus. So that's why we got this one. Interesting. Okay, write down this process by yourself on your A4 paper. Make sure you understand each step of the derivation. Camera off. Micro on. Next page. Now we have a real example. We have a beam. Then we have 2 piezoresistors. 1, 2. And this is wire connection. Metal, aluminum. Connect the 2 piezoresistors. Either are these 2 piezoresistors in series or parallel? Parallel or series? Bottom, can you help him? Are these 2 resistors in parallel connection or series connection? Series. Can you help him?
Because
Micro. Okay, so this is N-type silicon. Then we have P-type piezoresistor. Then 200 micro length, 20 micro width, 5 micro thickness. Then we have a load at this point. This is top view. So we have load at this point. Then we create tension to the P-type piezoresistors. Okay, next page. So we have the P-type pi L value and pi T value here. Remember the unit is 10 to minus 11th, 1 over Pascal. Heather, please read this whole paragraph.
From where I have to read?
From the beginning.
Make contact to the piezo resistor and it would be undesirable to have a competing transverse oriented resistor creating a cancelling effect.
Okay, stop. Previous. So this B we have pi L. And this one, if you use this one as a piezoresistor, because we have pi L. So this one is pi T. Remember, pi L is positive, pi L positive. Pi T, next page. Pi T is minus 660.3. So they will cancel out. So don't use pi T in this case. Okay, so then the piezoresistor length 20 micro, width 2 micro, thickness 0.2 micro. See, the piezoresistor thickness only 0.2, but the whole beam thickness 5 micro. So 0.2 is very, very small compared to 5 micro. So we assume the piezoresistor is on the top surface of the beam, and they have we just use the top stress for them. We don't consider the thickness of the piezoresistor. Okay, then the two piezoresistors. Then we have for cantilever beam with 1 point load at the end. This is the deformation as a function of x, previous. So this is x0. This is x equal to the total length, 200 micro. So this is the x coordinate. Next page. And W represents the deformation as a function of x. And LC is the total length, 200 micro. And x is the location along the beam. LC total length. And W max is the maximum deformation, previous. So this is the beam. We apply a load at the free end. So when x equal to 0, there's no deformation. W is 0. And at each point, W is different. And at this point, we have W maximum deformation. Next page. So W maximum represents the maximum deformation of the beam. So this is the solution for the deformation of the cantilever beam. Next. Curvature is W differentiation with respect to x twice. And we have this absolute value because now we just need the curvature. We don't need to define the positive curvature or negative curvature. It doesn't matter here. We just need the curvature value. Okay, so carry out this differentiation and prove the result is this one. Okay, please do the differentiation on your A4 paper and prove the result is this one. Steven, what happened to Frank? Police station too? Okay. Camera off. Micro on. Okay, then because the thickness 0.2 micro for piezoresistor is small compared to the whole thickness, so we can take only surface stress as the stress of the piezoresistor. Then on the top surface, remember we have sigma L equal to E over rho, H over 2 minus Z. But at the top surface, Z is either at the top surface, what's the value of Z? At top surface of the beam, what's the value of what the value of Z is. Like, could you tell him? Could you explain to him? Okay, because Z is 0, so we use this equation to calculate sigma L. And you got 1 over Z here already. So you plug this result to this equation, you can get the sigma L at the top surface. But remember, the length for the piezoresistor is 20 micro. 20 micro. So when x equal to 0, you can calculate the initial x equal to 0. You can calculate the initial stress of the piezoresistor. When x equal to 20 micro, you can calculate the stress at the location of 20 micro, and use the silicon Young's modulus 160 gigapascal for the value of E. And W maximum, we take W maximum as 1 micro. And LC is 20 micro. Okay, now please calculate this value, x equal to 0, and this value at x equal to 20 micro. Okay, do it by yourself to convince yourself the values is 30 megapascal and 27 megapascal. Yeah, do the calculation, please, everyone. Okay, camera off. Okay, camera on. Because for the piezoresistor, only 20 micro length. See, 30 micro, 30 megapascal, x0, and x20 micro is 27 megapascal. So it's not. We want to make our life easier. We just want to use one typical value. So if we want to use a typical value for stress value for this piezoresistor, which value will we use? The average 28.5 megapascal. We want to use this stress as the whole piezoresistor can be represented by this stress. Kaiser, which value of stress I'd like to use to represent the whole piezoresistor? Which stress value? So do you understand my English? Ethan, which stress value I'd like to use?
28.5.
Unit.
8 MPa.
Megapascal.
Megapascal.
Okay. So if we use 28.5 megapascal as the sigma L, and pi L is 71.8 times 10 to minus 11th. 1 over Pascal. So this one should be 1 over Pascal here. Then pi L times sigma L. Okay, please do the calculation to convince yourself the result is 0.02. Sigma L times pi L. Okay, camera off. Okay, let's go to next page. Motorola designed a pressure sensor based on this principle. Okay, next page. So this is the BZT. They use BZT in their CMOS circuit. Bipolar process. So basically, P-type substrate, then grow N-type on top of the P-type wafer. So this grow this N-type layer, then we create the P-type region, P-type region. Okay, next page. And this area is the BZT area. And this area is the MEMS area. We use the etching to create a cavity for air to come in. And this is the diaphragm, the N-type layer, and P-type piezoresistor for the pressure sensor. And this BZT plus, we have emitter, N-type emitter, and P-type base. And this is N plus collector. So it's a bipolar transistor for their device. Next page. Okay, next. Next. Okay, so this is the Motorola pressure sensor. This is the edge of the cavity. And piezoresistor here, they only use one piezoresistor. 45 degree with the inclined to the edge. And we have current goes in from this. This is current goes in from this point to this point. And we have voltage output. One tap and the other tap for voltage output. Voltage taps here and here. This one voltage, this one voltage. And the current goes in from this electrode, go to this electrode. And this is 110 direction on 100 wafer. So why is that? Because the etching process, let me explain again the etching. Okay, if this is 100 wafer, so this is 100 direction, then we create etching process, anisotropic etching. Remember, we have surface, 100 surface, 110 surface, 111 surface. On each surface, the atom density is different. The 111 surface has the maximum number of atoms compared to 110 and 100. So for the anisotropic etching process, the etchant will attack 100 surface, 110 surface, and the speed, etching speed, 111 is the slowest, 100 is the quickest, because 111 surface we have a lot of atoms there, so it's not easy to etch 111 surface. But it's much easier to etch 100 and 110 surface. Do you understand? Previous. Can you go to the page with the 3 surface? Yes. Okay, look at the atom. So 100 surface, you could count 1, 2, 3, 4. And for this atom, we can only count 1/4. 1/4 of this atom on this surface, because the other 3/4 belong to other surface. So 1/4 times 1, 2, 3, 4 equal to 1. So we have 1 atom on this surface. For this one, 110 surface, See, we have 1/4, 1/4, 1/4, 1/4, and 1. So total we have 2 atoms on 110 surface. Now 111 surface. We have this one, but for this one, so this is not a good representation. I don't have a good figure, but 111 surface, you can count. We have more atoms on 111 surface compared to 110 and 100 surface. 111 surface is the most dense, most populated surface. Okay, so that's why 111 surface is not easy to attack. And the angle between, okay, can you go to that page? Go back. Yes, see, this is 100 wafer. And so why this is 110 direction? Because remember, when we had H, anisotropic H, so this is 111 surface. So this is 111 direction. This is 100 direction. 111. So the interaction, this surface, this direction must be 110. So this direction normal to 100 and normal to 111. Suppose the value is A, B, C, and because this one and 100 perpendicular, so inner product is 0. So inner product is A plus B times 0 plus C times 0. So, and the other inner product for this vector and 111 vector, they are normal to each other. So A plus B plus C, because A times 1 plus B times 1 plus C times 1 is 0. And A equals 0, then B plus C equals 0. B equal to minus C. So the direction for this one is A is 0. B equal to minus C, you can assign any value to B. So if B is 1, C is minus 1. So this is 0, 1, 1 family. So that's why this is 110 direction. If you understand, raise your hand. Only one. Okay, Lan, help everyone to understand this one. What time is it? Okay, Lan, the stage is yours. Camera off.